Look up at the stars tonight, and you are seeing a cosmic lie. Every galaxy, every planet, every shimmering point of light adds up to less than 5% of what actually exists. The universe is not what it seems, and the true architects of reality are two invisible phantoms, dark matter and dark energy. By the end of this journey, you will have 25 mind-blowing facts that will permanently change how you see the cosmos. We will explore why galaxies do not fly apart, what force is ripping the universe to pieces, and whether our most fundamental laws of physics are wrong. What do you think is the most profound mystery waiting for us in the dark? Our entire reality is built on a foundation we cannot see. That 5% of normal matter, the stuff of stars and planets and life itself, is the rarest ingredient in the cosmic recipe. For every single atom in your body, there are 5 times as much dark matter surrounding you, and more than 13 times as much dark energy woven into the fabric of space itself. You are the cosmic exception, not the rule. This understanding did not come from a single brilliant insight, but from 2 profound puzzles that astronomers could not solve. The first clue appeared when scientists measured how fast stars orbit the centers of their galaxies. According to Newton and Einstein, stars on the outer edges should move slower, just as Pluto orbits our Sun much more sluggishly than Mercury. But the observations revealed something impossible. Those outer stars were racing around just as fast as the inner ones. It was as if the entire galaxy was embedded in a vast, invisible sphere of mass, a gravitational glue holding the speeding stars in place. They called this missing mass dark matter. The second, even stranger clue came from the afterglow of the Big Bang itself, the cosmic microwave background. This ancient light carries a precise fingerprint of the early universe, and by reading its patterns, scientists could calculate the total density of everything. The numbers they got were clear and shocking. Normal matter could only account for a sliver of the total. The rest, the overwhelming majority, was something else entirely. This is the famous cosmic pie chart, a humbling diagram that rewrote our place in existence. Picture an iceberg floating in a dark sea. The glittering tip above the water, the part that catches the light, that is everything we have ever seen or touched, every galaxy in every telescope. But beneath the surface lies an immense hidden bulk of dark matter, and the sea itself, the very space that holds the iceberg, is charged with the expansive force of dark energy. For all of human history, we have been meticulously studying the tip of the iceberg, unaware of the colossal, invisible reality it rests upon. What other fundamental truths are we missing simply because we have not yet learned how to look for them? This missing mass had to be something extraordinary, a substance that did not absorb, reflect, or emit light, yet exerted a powerful gravitational pull. We call this phantom force dark matter, and it acts as the universe's essential glue. Picture a child on a merry-go-round holding tight to a central post. If they let go, they are flung outward by centrifugal force. Now imagine that merry-go-round is a galaxy like our Milky Way. The stars on the outer spiral arms are moving at tremendous speeds, hundreds of kilometers per second. According to the laws of gravity we see in our solar system, there is simply not enough visible mass in the galaxy's center to hold onto those fast-moving outer stars. They should be flung off into the void, scattering the galaxy into a cosmic cloud of lonely stars, but they are not. Something invisible is holding them in their orbits, a vast halo of dark matter that envelops the entire galaxy like an invisible scaffold. This gravitational embrace is what keeps every spiral galaxy from spinning itself apart. The woman who proved this cosmic glue existed was astronomer Vera Rubin. In the 1970s, she meticulously studied the rotation curves of spiral galaxies, carefully measuring how fast stars orbited at different distances from the galactic center. Her data was undeniable and revolutionary. The stars far from the center did not slow down as predicted. Their speeds remained stubbornly high, a flat line on her graphs that defied Newtonian physics. The only logical conclusion was that galaxies contained enormous amounts of unseen matter, distributed far beyond their visible edges. Rubin's work provided the first robust observational evidence for dark matter, fundamentally challenging our understanding of the cosmos. She revealed that what we see is not what we get, that the true structure of the universe is shaped by an invisible hand. Her discovery was a quiet earthquake in astronomy, proving that the most dominant component of galaxies is something we cannot see at all. If dark matter is the glue, then what is the hammer that is tearing everything apart? While dark matter pulls the cosmos together, a far more mysterious force is pushing it apart. Dark energy is not a substance like dark matter, but a property of empty space itself, a kind of anti-gravity woven into the vacuum. Its effect is the exact opposite of dark matter's gravitational glue. It is a repulsive force causing the expansion of the universe to accelerate. For most of the 20th century, astronomers assumed the Big Bang's initial outward rush was gradually slowing down, pulled back by the collective gravity of all the matter in the cosmos. The great question was whether that slowdown would eventually lead to a big crunch, a collapse back into a single point, or if the universe would coast forever into a cold, dark stillness. Then, in 1998, two independent teams of astronomers made a discovery that shattered that entire paradigm and won them the Nobel Prize. They were measuring the distances to incredibly far-off supernova, stellar explosions so bright they can be seen across billions of light-years. By studying how much their light had stretched or redshifted, the teams could calculate how fast the universe was expanding at different points in its history. The results were not just surprising, they were universe-shattering. The distant supernova were dimmer than expected, meaning they were farther away than the old, slowing expansion model predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some unknown force was acting against gravity, pushing galaxies apart faster and faster as time went on. This was the moment dark energy entered the scientific lexicon. Think of it like this: you throw a ball straight up into the air. You expect gravity to slow it, stop it, and bring it back down. But instead, the ball not only keeps going up, it starts shooting away faster and faster, as if the air itself were propelling it upward. That is what dark energy is doing to our cosmos. It flipped our fundamental expectation of the universe's fate on its head. The question of a big crunch was answered with a definitive no, replaced by the prospect of a far lonelier end, a cold, empty expansion that may never stop. If dark energy is the accelerator, what is it made of, and why does empty space possess this strange, repulsive power? We have never seen a single particle of dark matter directly, yet we are absolutely certain it is there. How can we be so sure of something we cannot see? We detect it by the profound shadow it casts across the cosmos, by watching how it bends the very fabric of reality around it. One of the most powerful pieces of evidence comes from a phenomenon predicted by Einstein called gravitational lensing. Imagine space-time as a stretched rubber sheet and a massive object like a galaxy cluster as a heavy weight placed in the center. The weight creates a deep depression, a gravity well. Now, when light from a more distant galaxy travels toward us, it must pass near this depression. The light does not travel in a straight line, it follows the curved geometry of the warped sheet. From our perspective, the distant galaxy's image is distorted, stretched into long arcs, or sometimes even multiplied into several identical images around the foreground cluster. This is gravitational lensing, nature's magnifying glass. But when astronomers map these lenses, they often find that the amount of visible mass in the foreground cluster is not nearly enough to create the severe bending they observe. The only explanation is a huge amount of invisible mass, dark matter, deepening the gravity well and amplifying the lensing effect. We are literally seeing the ghostly silhouette of dark matter by watching how it bends the light from objects behind it. An even more dramatic and direct proof came from a cosmic crash site known as the Bullet Cluster. This is actually two giant clusters of galaxies that have collided, passing right through each other. During such a collision, the clouds of hot gas, which are the normal matter, slam together and slow down due to friction, like two clouds of smoke colliding. But the dark matter, which does not interact with anything except through gravity, would simply pass through unaffected. That is exactly what astronomers observed. Using X-ray telescopes, they mapped the hot gas which was stuck in the middle of the collision. Then, using gravitational lensing, they mapped the total mass, the gravity wells. The two maps did not match. The peak of the mass, the gravity, was not with the gas. It was in two separate clumps on either side where the galaxies themselves had traveled. This was a stunning snapshot, a cosmic fingerprint. It showed that most of the mass had sailed right through the collision, completely separate from the normal matter. We were not just inferring dark matter, we were seeing its shadowy outline clearly separated from everything else, proving it is a real, physical substance that moves through the universe like a ghost through walls. If we can map its shadow, what does its true nature feel like? The ghost we are chasing does not even belong to the familiar world of particles. A common guess is that dark matter might be made of antimatter, the exotic mirror image of normal particles. But this is a dead end, and the reason reveals just how strange dark matter truly is. Antimatter, for all its science fiction allure, is still normal matter. An anti-electron or positron has the same mass as an electron but a positive charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy, releasing a very specific signature of gamma rays. If dark matter were simply vast clouds of antimatter drifting through galaxies alongside normal matter, the universe would be filled with the constant, brilliant fireworks of annihilation. Our telescopes would see it everywhere, but they do not. The cosmos is not lit up by that telltale gamma ray glow. This means dark matter cannot be antimatter. It must be something fundamentally different, a substance that does not interact with light or with normal matter in any of the ways our standard model of particle physics describes. It does not feel the electromagnetic force at all, which is why it is dark. This fact is a crucial clue that narrows the search dramatically. We are not looking for a familiar particle wearing a disguise. We are hunting for something entirely new, a citizen of a hidden sector of physical reality. If it is not antimatter and not any particle we have ever seen, what could it possibly be? Another tempting idea lurks in the cosmic shadows. Perhaps dark matter is made of black holes. Not the giant monsters at galactic centers, but countless tiny, ancient ones, smaller than an asteroid, forged in the chaotic furnace of the Big Bang itself. These hypothetical primordial black holes could be drifting unseen through the galaxy by the trillions, their collective gravity providing the missing mass. It is an elegant and haunting solution, using objects we already know exist to solve a mystery we do not. For a time, this was a leading candidate. To test it, astronomers turned to a delicate technique called microlensing. The principle is similar to the large-scale gravitational lensing we discussed, but on a much finer scale. If a primordial black hole passed directly between us and a distant star, its gravity would act as a tiny lens, bending the star's light and causing it to briefly brighten before fading back to normal. By monitoring millions of stars for these telltale flashes, surveys could, in theory, count the invisible population of black holes. After years of meticulous observation, the results came back nearly empty. The number of microlensing events they detected was far too small to account for all the dark matter. The universe is simply not swarming with enough of these ancient black holes to be the answer. A second definitive blow came from an entirely different kind of observatory, one that listens to the ripples in space-time itself. When black holes merge, they send out powerful gravitational waves. If dark matter were primarily made of primordial black holes, mergers between them would be common events in the history of the universe. Our gravitational wave detectors, like LIGO and Virgo, should be hearing a constant, crowded chorus of these collisions from the distant past. But the cosmic soundtrack is not that loud. The merger rate we observe is quiet, consistent with the rare meetings of stellar black holes from dead stars, not a vast sea of primordial ones. These two independent lines of evidence, the silent skies and the quiet ripples, have largely closed the door on black holes as the main component of dark matter. This exclusion is actually a profound step forward. It forces us to look beyond known physics toward something truly exotic and undiscovered. The hunt must now focus on particles that have never been seen, theoretical entities that could form the vast, invisible scaffold of reality. What kind of particle could be everywhere yet interact with nothing? The hunt for this ghostly particle has settled on a prime suspect, a theoretical entity with a name that sounds like a character from a physics comic book, the WIMP. WIMP stands for Weakly Interacting Massive Particle, and it is the leading candidate to explain the dark matter mystery. The name itself is a perfect description of its proposed nature. It is massive, meaning it has a significant weight, perhaps dozens or even hundreds of times heavier than a proton. More importantly, it is weakly interacting. This means it completely ignores the electromagnetic force, so no light touches it, and it brushes right through normal matter almost all the time. Its only known interactions would be through gravity, which is how we feel its presence, and possibly through the weak nuclear force, the same force responsible for radioactive decay. This weakness is both the reason it has remained hidden and the slim chance we have of finding it. Imagine trying to catch a ghost that can pass through solid lead as if it were empty air, a phantom that only very, very rarely leaves a fingerprint on the material world. That is the monumental challenge of detecting a WIMP. To have any hope of catching such an elusive particle, scientists have gone to extraordinary lengths, literally descending into the Earth. Deep underground, in abandoned mines and beneath mountains, they have built the quietest, most shielded laboratories on the planet. Experiments with names like LUX Zeppelin and Xeno NNT are the ultimate traps. They consist of huge vats often filled with tons of ultra-pure liquid xenon, kept in cryogenic darkness. The idea is to wait with unimaginable patience for the one in a trillion event where a passing WIMP from the Milky Way's dark matter halo might actually bump into the nucleus of a xenon atom. This tiny collision would produce a faint flash of light and a wisp of electrical charge, signals so subtle they could be drowned out by a single cosmic ray from the sun or a trace of natural radioactivity in the surrounding rock. That is why these detectors are buried under a mile of solid rock to shield them from the constant background noise of the universe. For decades, these silent sentinels have been listening, watching, waiting for a whisper from the dark. They have not heard one yet. Every year, the experiments grow larger and more sensitive, ruling out whole classes of possible WIMP by their silence. This lack of a signal is not a failure. It is a process of elimination, narrowing the search and telling us what dark matter is not. But if WIMP are not speaking to us in these deepest of dungeons, could the answer lie in a particle so light it dances on the edge of existence? The silence of the WIMP detectors has forced physicists to broaden the search, to consider candidates that are not just elusive but almost ethereal. Enter the action, a particle born from a problem so fundamental it questions the symmetry of reality itself. While WIMP are heavy and rare, actions are the opposite. They could be billions of times lighter than an electron. So light they would exist in unimaginable numbers, flowing through the universe not as discrete bullets but as a pervasive cosmic wave. Their origin story is not dark matter but a deep mystery within the strong nuclear force, the glue that holds atomic nuclei together. Physicists call this the strong CP problem. In simple terms, the equations that describe the strong force allow for a certain kind of asymmetry that should make particles like the neutron behave differently than their mirror images. This asymmetry would have profound effects, potentially even preventing complex atoms from forming. Yet, when we look at the neutron with incredible precision, this asymmetry is utterly absent. It is balanced to a degree that seems unnaturally perfect, as if a hidden hand dialed a fundamental constant of nature to zero. To explain this eerie perfection, theorists proposed a new particle, the action, a kind of cosmic correction that naturally sweeps this problematic asymmetry under the rug. In solving one profound puzzle, they accidentally created the perfect candidate for another. If actions exist, they would have been produced in colossal numbers in the hot dawn of the universe, and their collective mass could easily account for all the dark matter we observe. They would be everywhere, a ghostly ocean through which we all swim. Detecting an action, however, is a challenge of exquisite subtlety. Since they are so light and interact so feebly, you cannot wait for one to bump into an atom. Instead, you must coax it to reveal itself. The most promising experiments, like the Action Dark Matter experiment or ADMX, use a strategy that feels like alchemy. They employ a powerful superconducting magnet, creating an intense magnetic field inside a resonant cavity, a kind of ultra-precise microwave oven. The theory predicts that in the presence of such a strong magnetic field, a passing action from the dark matter halo could spontaneously convert into a single, faint photon of microwave light. The experiment then tunes its cavity across millions of frequencies, listening intently for one specific note, a whisper of microwave energy that appears from nowhere. It is the ultimate cosmic radio, scanning for a station broadcast by the fabric of dark matter itself. The search is painstakingly slow, a frequency-by-frequency hunt for a needle in a haystack the size of the universe, but a single, clear signal would be a discovery of monumental proportions. It would not only identify the dark matter particle, but also solve a 40-year-old mystery at the heart of nuclear physics in one breathtaking moment. So we hunt for both the heavy and the impossibly light, the rare collision and the faint universal hum. But what if the answer is not a particle at all, but a flaw in our most cherished theory of gravity? The search for a single ghostly particle might be missing the forest for the trees. What if dark matter is not just a simple substance, but the foundation of an entire hidden universe operating by its own secret set of physical laws? This is the breathtaking speculation behind our ninth fact. Dark matter might have its own dark force. We have always assumed dark matter is simple and inert, only capable of feeling gravity. But what if, within its own invisible realm, it experiences a rich and complex physics all its own? Theorists propose the existence of a dark electromagnetic force carried by hypothetical dark photons. Just as normal photons mediate light and electricity for our world, dark photons could allow dark matter particles to interact with each other, to attract and repel, to form intricate structures we can barely conceive. They could have their own version of chemistry, a shadow physics playing out in perfect silence right alongside our own. This idea is not pure fantasy, it is motivated by real puzzles in the data. For instance, some computer simulations of how dark matter halos should form around galaxies predict very dense, cuspy centers. Yet observations of actual galaxies often suggest smoother, more spread out cores. It is a small but persistent discrepancy. One elegant solution is if dark matter particles can interact with each other through this dark force. This self-interaction would act like a kind of pressure, smoothing out those dense cusps into the gentler cores we seem to see, like an invisible hand stirring the dark matter pot. The implications are staggering. If dark matter can interact and clump through its own forces, then it could form objects entirely separate from normal matter. Imagine dark stars, colossal spheres powered not by nuclear fusion, but by the annihilation of dark matter particles within their own hidden hearts. Picture entire dark galaxies, vast assemblies of dark matter that never ignited a single visible star, ghost islands adrift in the cosmic sea, completely invisible to every telescope ever built. They would reveal themselves only by the subtle tug of their gravity, bending the light from more distant objects that pass behind them. We may already be seeing hints of these structures in the faint, unexplained gravitational lenses that dot our sky maps. This transforms dark matter from a passive glue into the substance of a parallel cosmos, a silent twin to our own glittering universe of light. The question then becomes haunting. If a dark galaxy formed, could a form of dark life ever evolve within it, forever unaware of our shining reality, just a gravitational whisper away? That shadow universe of dark matter is not a formless cloud. It is the master architect of everything we see. The grandest structure in all of existence, the cosmic web, is its blueprint made real. Look at a map of the universe on the largest scales, a survey of millions of galaxies. You will not see a random scattering of lights. Instead, you will witness an intricate, breathtaking architecture, a vast network of brilliant filaments and walls connecting dense knots of galaxy clusters, all surrounding unimaginably vast, empty voids of near-total nothingness. This is the cosmic web, and it is not built by stars. It is woven by the gravitational hand of dark matter. In the first moments after the Big Bang, the universe was a nearly smooth soup of matter and energy. But it was not perfectly smooth. Thanks to quantum fluctuations, tiny seeds of density existed, microscopic ripples in the fabric of the newborn cosmos. Dark matter, responding only to gravity, began to clump around these seeds. Because it does not feel pressure or radiation, it could start collapsing long before normal matter, which was still a searing plasma buffeted by light. Over hundreds of millions of years, these dark matter clumps grew, merging and attracting more mass, carving out vast gravitational basins in the expanding universe. They formed an invisible skeleton first, a three-dimensional scaffold of filaments and nodes. Then, the normal matter, the future stars and galaxies, had no choice but to follow. As the universe cooled, atoms could finally form, and this gas began to flow along the gravitational highways laid down by the dark matter. It cascaded into the deepest wells of this invisible framework, piling up at the intersections of filaments, where it eventually condensed, ignited, and lit up as the galaxies and brilliant clusters we observe. We are not seeing the primary structure, we are seeing the decoration. The glittering galaxies are like streetlights outlining the shape of an invisible city, tracing the contours of a dark matter metropolis whose scale defies human comprehension. The voids, those terrifyingly empty regions spanning hundreds of millions of light years, are not accidents. They are the inverse of the web, the territories where dark matter was scooped out by gravity, leaving behind a cosmic desert where normal matter had nothing to cling to. This means every galaxy, every cluster, every thread of light in the deepest telescope image is a prisoner of gravity, following a map drawn by a substance we cannot see. Our Milky Way is not floating freely in space. It is riding a dark matter current, moving along a filament toward the immense gravitational pull of the Great Attractor, itself a node in this grand design. The beauty of the night sky is a magnificent after-effect, a luminous echo of a dark structure that decided the fate of the cosmos before a single star was born. The greatest blunder in scientific history was not a mistake but a prophecy. Albert Einstein, wrestling with his own theory of general relativity in 1917, faced a problem. His beautiful equations described a dynamic universe, one that should either be expanding or contracting under gravity. Yet, the scientific consensus of his time insisted the cosmos was eternal and static. To force his theory into this mold, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant, represented by the Greek letter lambda. This constant was a repulsive energy, a kind of anti-gravity woven into the very fabric of empty space, perfectly balanced against the attractive pull of matter to hold the universe in a steady state. When Edwin Hubble later proved the universe was indeed expanding, Einstein famously discarded the constant, calling it his greatest blunder. He had invented the perfect solution, then thrown it away for the wrong reason. Now, nearly a century later, the ghost of lambda has returned with a vengeance. The discovery of the accelerating universe in 1998 demanded an explanation, and the simplest, most elegant one was already written in Einstein's old equations. The cosmological constant is now the leading candidate for dark energy. It is not a blunder, but perhaps his most stunning intuition. This idea proposes that dark energy is not a changing field or a new force, but a fundamental property of the vacuum. Empty space, according to quantum physics, is not truly empty. It is a seething, bubbling foam of virtual particles that constantly flicker in and out of existence. This quantum activity endows every tiny cubic centimeter of nothingness with a tiny, intrinsic energy. The cosmological constant suggests this vacuum energy has a positive value, a constant energy density that permeates all of space. And because it is a property of space itself, as the universe expands and more space is created, more of this repulsive energy comes into being. This leads to a runaway effect where the push of dark energy grows stronger relative to the pull of matter, causing the expansion to accelerate faster and faster over time. Think of it like a peculiar kind of interest on a cosmic loan. Imagine you borrow money, and the interest you owe is not calculated on the principal, but on the growing amount of empty space in the bank vault. As the vault expands, your debt grows exponentially, and you can never hope to pay it back. That is the relentless logic of the cosmological constant. It is a beautifully simple idea, but it comes with a devastating problem. When physicists try to calculate the expected strength of this vacuum energy from quantum theory, their number is catastrophically wrong. It is off by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. This means either our understanding of quantum vacuum energy is profoundly incomplete, or the cosmological constant is not the final answer. Einstein's ghost offers a solution, but in doing so, it points to a chasm in our knowledge so vast it threatens to swallow our most fundamental theories whole. Einstein's cosmological constant is a hauntingly simple answer, but its staggering mismatch with theory leaves a door wide open for something far stranger. Perhaps dark energy is not a static property of space, but a dynamic, evolving entity. This is the essence of quintessence, the leading rival to lambda. The name itself is a nod to ancient philosophy, where it referred to a fifth element beyond earth, air, fire, and water, a celestial substance filling the universe. In modern cosmology, quintessence proposes that dark energy is not a constant, but a field, a kind of cosmic fluid that permeates all of space. Unlike the unchanging cosmological constant, this field can change in density and push over time. In its simplest form, you can think of it as a kind of cosmic weather. The strength of its repulsive force could have been different in the past, and it might change again in the distant future. This is a fundamentally different vision of cosmic fate. With a cosmological constant, the acceleration is a one-way ticket to an ever faster, ever colder expansion. But with quintessence, the story could have dramatic twists. One possibility is that the field could eventually decay, its repulsive power fading away, allowing gravity to once again become the dominant force on cosmic scales. Another, more unsettling possibility is that the field could strengthen, leading to a runaway acceleration so extreme it would eventually overcome all other forces, tearing apart galaxies, solar systems, and even atoms themselves in a far future cataclysm called the Big Rip. The key to unlocking this mystery lies in measuring the history of the universe's expansion with exquisite precision. Astronomers are not just looking at distant supernova anymore, they are building a three-dimensional map of the cosmos. By combining observations of millions of galaxies and the faint imprint of sound waves frozen into the early universe, known as baryon acoustic oscillations, they can measure how fast space was stretching at different epochs. The goal is to see if the acceleration has been steady, as a constant would predict, or if it has changed over billions of years. A changing acceleration would be the smoking gun for quintessence. It would mean dark energy has a history, a biography we can read in the light of ancient stars and the large-scale architecture of the universe. We are not just asking what dark energy is, we are asking if it has a memory and whether the fate of everything is written in stone or is still being written by a field we are only beginning to sense. Our ultimate destiny is written in a single number, a value so crucial it is known as the equation of state. This number, represented by the letter W, describes the pressure dark energy exerts relative to its energy density. It is the dial that controls the fate of everything. If dark energy is Einstein's cosmological constant, a true and unchanging property of the vacuum, then W equals exactly -1. This simple, steady push leads to a specific and somber end, the big freeze or heat death. In this future, the acceleration continues at a relentless but constant rate. Galaxies outside our own local group will first redden, then fade from view as the space between us stretches faster than light can cross it. Billions of years from now, the Milky Way will merge with Andromeda to form a single, aging giant galaxy, an island in an ever-darkening sea. Within it, stars will slowly burn through their fuel. New star formation will cease as the last clouds of gas are either used up or expelled into the void. One by one, stars will wink out from the brilliant blue giants to the long-lived red dwarfs. Planets will grow cold and dark. Black holes will slowly evaporate over unimaginable eons through Hawking radiation. The universe will approach a state of maximum entropy, a uniform, frigid darkness where the temperature everywhere approaches absolute zero, and no energy gradient remains to power any process, any thought, any flicker of change. It is a quiet, eternal end, but what if that dial is turned just slightly? If dark energy is a dynamic quintessence field that grows stronger over time, then W is less than -1, a condition physicists call phantom energy. This scenario unleashes the most violent cosmic finale imaginable, the Big Rip. Here, the repulsive force does not just accelerate expansion, it grows in strength exponentially. About 60 million years before the end, phantom energy would overcome the gravity binding our local group of galaxies, tearing our merged Milky Way Andromeda galaxy apart. Stars would be flung into the expanding void. Roughly 3 months before the final moment, the phantom force would rip apart our solar system. In the last minutes, it would shatter Earth itself. In the final infinitesimal fraction of a second, the repulsion would overcome the electromagnetic and nuclear forces holding atoms together, and then the very fabric of space-time would be torn asunder. The universe would end not with a whimper but with a catastrophic rupture of reality itself. Between these two extremes lies a third, more gentle possibility. If quintessence weakens over time, W could be greater than -1. The acceleration might slow or even reverse. Gravity could reassert its dominance, potentially leading to a big crunch where the universe stops expanding and begins to collapse back in on itself, perhaps leading to a new Big Bang in an endless cycle. Every measurement we make of distant supernova, of galaxy clustering, of the cosmic microwave background, is an attempt to read that dial, to measure W with enough precision to know which story is ours. We are, in a very real sense, reading the last page of the cosmic book to see how it ends. The unsettling truth is that the force deciding the fate of every atom, every star, and every galaxy is one we have only just discovered and whose fundamental nature remains a complete mystery. This timing is not an accident, it is a cosmic riddle that keeps cosmologists awake at night. We live in a special moment, a brief window in the 14 billion-year history of the universe where dark matter and dark energy are locked in a strange, delicate balance. Their energy densities, their influence on the expansion of space, are of the same order of magnitude right now. But this was not always true, and it will not be true for long. This is the profound coincidence problem, and it asks a haunting question: why are we here to see it? For most of cosmic history, dark matter was the undisputed ruler. In the early, dense universe, its gravitational pull dominated, slowing the expansion and sculpting the cosmic web. Dark energy, if it existed as a constant, was an insignificant whisper, a tiny fraction of the total energy budget, utterly overwhelmed by matter's gravity. For billions of years, the universe was matter's domain. But as the cosmos expanded and thinned out, the density of matter dropped, the gravitational brake began to weaken. Meanwhile, if dark energy is a property of space itself, its density remained constant. Imagine a race where one runner gets slower and slower as the track stretches, while the other maintains a steady, relentless pace. There comes a point where the second runner finally catches up. That moment, about 5 billion years ago, is when dark energy's repulsive push finally matched and then surpassed the gravitational pull of all the matter in the universe. That is when the acceleration began. We now live in the brief transitional epoch where the two titans are roughly equal in influence, but this balance is fleeting. Dark matter's density will continue to plummet as space grows, while dark energy's influence will soar. In the far future, dark energy will be almost everything, and dark matter will be a fading memory. So why do we find ourselves in this cosmic sweet spot, this narrow sliver of time when both forces are comparable? One unsettling possibility is the anthropic principle, the idea that the universe must be compatible with the existence of observers like us. If dark energy had been much stronger earlier, it would have blown the universe apart before galaxies could ever form. No stars, no planets, no us. If it were much weaker or even attractive, the universe might have collapsed in a big crunch long before intelligent life could evolve. We can only exist in a universe where the numbers allow our kind of complexity to arise, and that may naturally place us in this era of balance. It is a selection effect. We are here to ask the question because the conditions allowed us to be. But many physicists find this answer deeply unsatisfying. It feels like giving up on a deeper explanation. They suspect a more fundamental link, a hidden law of physics that actually ties the densities of dark matter and dark energy together, making their coincidence not an accident of timing, but a necessary feature of the cosmos. Perhaps they are two sides of the same coin, different manifestations of a single, underlying field we do not yet understand. Solving this riddle is more than academic. It is a search for the reason we are here at all, in this specific moment of cosmic history, witnessing a duel between two invisible giants that defines the fate of everything. The nature of this invisible architect comes down to its speed. Was dark matter born racing across the newborn universe at nearly the speed of light, or did it lumber into existence slow and cold? The answer is written in the very structure of the galaxies we see today, and it points overwhelmingly to a slow, cold beginning. This is the foundation of the cold dark matter model, the reigning theory that has shaped our understanding of cosmic evolution. In physics, cold does not mean a temperature you can feel, it refers to speed. Cold dark matter particles would have been moving sluggishly at a tiny fraction of light speed when the first structures began to form. This slowness was absolutely critical. Think of it like trying to build a sandcastle. If you throw dry, fine sand, it scatters on the wind. But if you use wet, heavy sand, it clumps together easily, sticking to itself to form mounds and towers. Cold dark matter is the wet sand of the cosmos. Its lethargic motion allowed it to readily collapse under its own gravity into tiny, dense clumps, even before the universe was 1 billion years old. These microscopic seeds, these first halos of pure dark matter, were the gravitational anchors for everything that followed. Gas, the normal matter, flowed into these small wells, pooling and igniting to form the very first minuscule proto-galaxies. Then, over billions of years, a cosmic hierarchy emerged through relentless mergers. Those small dark matter halos with their captive stars and gas collided and combined, building up into larger and larger structures, eventually forming the majestic spiral galaxies and colossal clusters we observe. This bottom-up formation from small to large is a stunning prediction of the cold dark matter model, and it matches the observed universe with remarkable precision. But what if dark matter was hot? This alternative model imagines particles like neutrinos, which are born moving at almost the speed of light. This frenetic energy is a problem. Fast-moving particles are cosmic smoothing agents. They resist clumping on small scales. A universe dominated by hot dark matter would have formed the largest structures first, like superclusters, and only later fragmented into galaxies. It is a top-down scenario, like a vast cosmic sheet shattering into shards. The fatal flaw is that there would not have been enough time for the small, dense galaxies we see in the early universe to form at all. The observed cosmos is simply too lumpy on small scales, too rich with dwarf galaxies and intricate filaments for hot dark matter to be the main ingredient. Warm dark matter, a hypothetical middle ground, is not ruled out entirely, but it too struggles to explain the abundance of the very smallest galactic structures we are now finding. The incredible success of the cold dark matter model is why we picture it as a slow, massive, and fundamentally clumpy substance. Its glacial pace in the ancient past set the rhythm for all of creation, allowing the universe to build itself from the ground up, one invisible brick at a time. But if it is so successful, why are we finding cracks in its foundation at the smallest scales? The very success of the cold dark matter model has revealed a glaring mismatch, a ghostly absence where our simulations predict a teeming crowd. This is the missing satellite problem, a cosmic census that came up disturbingly short. When physicists run supercomputer simulations of how a galaxy like our Milky Way should form from cold dark matter, they get a very specific prediction. Our galaxy should be surrounded by a vast swarm of thousands of smaller dark matter clumps called subhalos. These are the leftover building blocks, the small lumps of dark matter that never fully merged into the larger halo. Gravity dictates they should be there, orbiting our galaxy like a cloud of invisible moons. The logical next step was to look for the small, faint dwarf galaxies that should be living inside these subhalos, using the trapped gas and stars as luminous beacons. But when astronomers completed the count, the numbers did not match. We have found only a few dozen of these satellite dwarf galaxies, not the many thousands the simulations suggest. It is as if we predicted a bustling metropolis of neighborhoods but found only a handful of isolated villages. So where is everyone? The most likely answer is that the dark matter subhalos are all there, just as the simulations show. But the vast majority of them are completely, utterly dark. They failed to light up with stars. There are two compelling reasons for this cosmic blackout. First, consider the scale. The smallest predicted subhalos are incredibly tiny, with masses perhaps only 1 million times that of our Sun. Their gravitational grip is very weak. In the early, violent universe, filled with intense radiation from the first stars and galaxies, the feeble gas that might have fallen into these small halos could have been easily blasted away or heated up so much it could never cool and condense to form stars. It is like trying to light a campfire in a hurricane. The flame is simply snuffed out before it can catch. Second, even if some gas did settle, the very first supernova in these proto-galaxies could have been powerful enough to blow all the remaining star-forming fuel clear out of the shallow gravitational well, permanently sterilizing the subhalo. The result is a universe filled with invisible dark matter islands, failed galaxies that never got the chance to shine. We may already have indirect proof they exist. Some astronomers point to mysterious, repeated bursts of gamma rays or distortions in streams of stars within our own galaxy, suggesting the gravitational tug of unseen, massive objects passing by. These could be the footprints of the missing satellites, dark halos moving silently through our cosmic neighborhood. The problem is not that the dark matter is missing, it is that the light we expected to trace it never turned on. This forces us to refine our understanding of galaxy formation, reminding us that dark matter provides the scaffold, but the complex, messy physics of normal matter, of gas and radiation and explosions, decides what gets to glow. If most of the universe's building blocks are these dark, silent islands, what does that mean for our search to finally touch the invisible architecture itself? The most important photograph in the history of the universe is a map of static. It is a snapshot of the cosmos at just 380,000 years old, an infant taking its first breath of light. This is the cosmic microwave background, the CMB, and it is the ultimate baby picture, a faded glow that fills every direction of the sky. To understand it, you must rewind time to a moment before stars, before galaxies, before atoms as we know them. The entire universe was a seething, opaque plasma, a thick fog of protons, electrons, and light, so dense that photons could not travel any distance without crashing into a particle. Then, as expansion cooled the cosmos, a pivotal moment arrived. Electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the fog cleared. The light, which had been trapped for eons, was finally set free. That first flash of liberated light has been traveling ever since, stretched by the expanding universe over 13 billion years from visible blaze into the faint microwave whisper we detect today. This afterglow is not perfectly smooth. When we look at it with exquisitely sensitive instruments like the European Space Agency's Planck satellite, we see a mottled map of tiny temperature variations, mere millionths of a degree. These are not random imperfections, they are the fossilized imprints of the earliest quantum ripples, magnified to cosmic scale by inflation. Those slightly denser patches, those microscopic hotspots in the infant plasma, were the gravitational seeds where dark matter had already begun to pool. They held the blueprint for everything to come, but the CMB is far more than a fossil, it is a precise cosmic ledger. The exact pattern of those hot and cold spots, their size distribution across the sky, is a mathematical fingerprint that encodes the universe's vital statistics. By measuring this pattern with incredible accuracy, cosmologists can run the equations of our best models backward, asking what ingredients and in what proportions are required to produce the exact map we see. The answer it gives is definitive and humbling. The CMB tells us that normal matter, the atoms in stars and planets, makes up only about 5% of the cosmic budget. It tells us that dark matter, the gravitational scaffolding, must constitute roughly 27%, and it tells us that the remaining 68% must be in the form of dark energy, the component needed to make the overall geometry of the universe flat and to match the large-scale patterns we observe. This single, ancient photograph is our most powerful evidence for the precise recipe of reality. The whispers of quantum noise from the first moment have, over billions of years, written the entire history of cosmic structure into a pattern of cold and warm that we can now decode. It is the universe's first cry, and in its echo, we hear the names and the proportions of the invisible giants that have shaped our existence. But what if we have been reading the cosmic ledger all wrong? The entire edifice of dark matter rests on one unshakable pillar, our trust in Einstein's theory of gravity. But a small, persistent group of physicists asks a radical question: what if gravity itself is the phantom? Their proposal throws out the need for invisible matter entirely and suggests instead that our equations of gravity are incomplete. This idea is called modified Newtonian dynamics, or MN. Its logic is beautifully simple, and in certain places it works with startling elegance. The core claim of Mund is that gravity does not follow Newton's inverse square law or even Einstein's field equations in all circumstances. Instead, at extremely low accelerations, like those experienced by stars on the fringes of a galaxy, gravity gets a subtle boost. It becomes stronger than our standard formulas predict. This extra gravitational kick, baked into the law of physics itself, would be enough to hold those fast-orbiting outer stars in place without invoking any dark matter at all. For individual, isolated galaxies, Mund is a stunning success. It can match the observed rotation curves of spiral galaxies with remarkable precision using only their visible stars and gas. It predicts specific relationships between a galaxy's brightness and its rotation speed, relationships that are often borne out by observation. For its proponents, this is Occam's razor in action. The simplest solution is to change the force law, not to invent an entirely new, invisible form of matter that constitutes 85% of the universe. Why conjure a cosmic ghost when you can just fix the map? The appeal is undeniable, a single, elegant tweak to physics that solves the galaxy rotation problem at a stroke. But the universe is a relentless examiner, and Mund faces two devastating challenges that dark matter sails through. The first is the bullet cluster, that cosmic collision we discussed earlier. Remember, the gravitational lensing map showed the mass had sailed right through the crash, separate from the normal matter. Mund, which modifies the relationship between visible mass and gravity, has a profound problem here. The gravity is not where the visible matter is. To explain this, even Mund theories must invoke some form of unseen, collisionless mass, something that looks suspiciously like a form of dark matter. This forces the theory into a corner. Either it is not a complete replacement, or it needs complex, ad hoc additions that strip away its initial simplicity. The second, and perhaps fatal, blow comes from the cosmic microwave background. The intricate pattern of hot and cold spots in that ancient light is a precise test of how structure forms in the universe. The standard model of cosmology, with cold dark matter and dark energy, reproduces this pattern with breathtaking accuracy. Mund on its own cannot. The early universe before galaxies formed was a smooth, high-density place where accelerations were not low. In that environment, Mund modifications would not operate, and without dark matter's gravitational seeds to amplify the tiny quantum fluctuations, the model cannot produce the rich, detailed cosmic web we see imprinted on the CMB. It cannot build the universe from the ground up. To salvage the theory, some researchers have developed relativistic versions of Mund, like TVS, which attempt to incorporate these cosmological needs. But these theories often become more complex and less elegant than the dark matter model they seek to replace, and they still struggle to match the full suite of data. The battle between Mund and dark matter is not a fringe debate, it is a fundamental clash of scientific philosophies. Do we keep our trusted laws of gravity and invent new substances to fit the data, or do we rewrite the laws themselves? For now, the weight of evidence, from colliding clusters to the whisper of the Big Bang, leans overwhelmingly toward the existence of a dark, massive something. But the persistence of Mund is a vital reminder that science must always question its foundations, and that the true nature of gravity, the architect of reality, might still hold secrets waiting in the faint, slow orbits at the edge of every galaxy. Billions of silent phantoms are streaming through you at this very moment. The dark matter halo enveloping our galaxy is not a distant abstraction, it is a local, pervasive presence. Based on the best estimates of its density in our cosmic neighborhood, physicists calculate that your body is being traversed by something like 1 billion dark matter particles every single second. This is not a metaphor, it is a physical reality as constant as your own heartbeat. Picture the gentlest, most invisible rain imaginable, a downpour of ghostly matter that began falling when the first galaxies formed and has continued unabated for billions of years. It falls on cities and forests, oceans and mountains, passing through every barrier, every vault, every living thing without the slightest hesitation. You are standing in that rain right now, and you always have been. The reason you feel nothing, the reason no instrument has ever definitively registered a single one of these particles from within you, is their profound weakness. They are the ultimate ghosts. A dark matter particle interacts so feebly with normal matter that it can pass through a light year of solid lead as if it were empty space. Your body, and indeed our entire planet, is utterly transparent to this silent storm. They enter through the top of your head, sail through the empty spaces within your atoms, and exit through the soles of your feet, continuing their journey into the Earth's core and out the other side into the void, all in a fraction of a blink. This transforms the mystery from a distant cosmic puzzle into an intimate, personal experience. The same invisible substance that sculpted galaxies and dictates the fate of the universe is here, now, mingling with the very atoms that constitute you. You are, in a literal sense, a temporary meeting place for the cosmos. Every breath you take contains not just nitrogen and oxygen, but the silent, unmoving presence of the universe's dominant material. It is a connection as profound as it is undetectable, a reminder that we are not just observers of the cosmos, but participants, woven into its deepest fabric by a rain of ghosts we are only beginning to dream of detecting. Our silent, ghostly rain may be invisible, but its effects are not, and we are now building a machine in the void to trace its every contour. The European Space Agency's Euclid Space Telescope is humanity's most ambitious attempt to map the invisible architecture of the cosmos. Launched in July of 2023, this extraordinary observatory is not looking for a single particle, but for the grand shadow that dark matter and dark energy cast across the entire sky. Its mission is breathtaking in scope: to create the largest and most precise three-dimensional map of the universe ever made, charting the positions and shapes of billions of galaxies across 10 billion years of cosmic history. Think of it as taking a cosmic census on an unimaginable scale, not just to count the lights, but to measure the hidden forces bending the space between them. Euclid carries two powerful instruments. One captures razor-sharp visible light images over an area of sky hundreds of times larger than the full moon in a single shot. The other is a near-infrared spectrometer, capable of measuring how much the light from each of those distant galaxies has been stretched by the expansion of the universe, which tells us its distance. By combining these two pieces of information, position and distance, Euclid will construct a staggering 3D model of the cosmos, but the real magic lies in what it does with the shapes of those galaxies. As light from distant galaxies travels to us, it passes through the vast, invisible webs of dark matter that warp space-time. This gravitational lensing distorts the galaxy's images, stretching them into subtle, elongated arcs. By measuring these tiny distortions across billions of galaxies, Euclid will essentially perform a cosmic tomography scan. It will trace the distribution of all the mass in the universe, both visible and, crucially, dark. This will give us our first high-resolution picture of the cosmic web in 3 dimensions, revealing the dark matter skeleton in unprecedented detail. The data will be a brutal test for our theories. Does the web structure match the predictions of cold dark matter and Einstein's gravity? Or does it show signs of something else, like modified gravity or self-interacting dark matter? Simultaneously, by measuring how the clustering of galaxies has changed over cosmic time, Euclid will track the expansion history of the universe with phenomenal accuracy. This is our direct probe of dark energy's behavior. Has the strength of this repulsive force remained constant, as Einstein's cosmological constant suggests, or has it varied over billions of years, pointing to a dynamic field like quintessence? Euclid's 6-year mission will provide the data to answer these questions, offering a definitive check on the recipe of reality we have deduced from the cosmic microwave background. It is not alone in this new golden age of cosmology. NASA and Nancy Grace Roman Space Telescope, launching later this decade, will conduct a similar wide-field survey, adding its own immense power to the effort. Together, these observatories are not just telescopes, they are time machines and cartographers for the unseen. They are building the map that will show us for the first time the true landscape of the universe, a geography drawn not in light but in gravity and shadow. The silent maps of Euclid and Roman will chart the present universe, but to understand the very first moments of structure, we need a time machine that can look back to the dawn of light. That machine is the James Webb Space Telescope, and its golden eye is now staring directly into the cosmic dark ages. This is not about seeing dark matter, but seeing its first and most profound handiwork. The Dark Ages refer to the period after the cosmic microwave background faded, but before the first stars and galaxies ignited, a time when the universe was a vast black sea of neutral hydrogen, punctuated only by the invisible gravitational wells of dark matter. Webb's unparalleled infrared vision allows it to detect the light from the very first galaxies that ended this darkness. Galaxies so distant their light has been traveling for over 13 billion years. When Webb captures the faint glow of these infant star systems, it is not just looking at ancient stars, it is seeing the imprint of the dark matter halos that birthed them. The size, brightness, and clustering of these primordial galaxies are direct reports from the front lines of cosmic construction. They tell us how quickly dark matter began to clump after the Big Bang. If the earliest galaxies Webb sees are surprisingly small and numerous, it would support the cold dark matter model, where slow-moving particles clumped efficiently into many small halos. If, however, the first galaxies appear fewer, larger, and more spread out, it could be a hint of warm dark matter, where faster-moving particles smoothed out the small-scale structures, delaying galaxy formation. Every pixel in Webb's deepest images is a clue in this cosmic detective story. By counting these first galactic sparks and measuring how they are grouped together across the void, astronomers can essentially weigh the smallest dark matter halos that ever existed. It is like finding the footprints of an invisible giant by studying the pattern of the first raindrops that fell into its footprints. Webb's observations are already challenging expectations, revealing galaxies that are brighter and more mature in the very early universe than many models predicted. This could mean that dark matter halos formed stars with astonishing efficiency, or it might point to subtler properties of dark matter itself, perhaps a slight ability to interact and dissipate heat, allowing gas to cool and collapse into stars even faster. With each new deep-field image, Webb is rewriting the first chapter of galactic history, and in doing so, it is refining the recipe for the invisible ingredient that wrote the book. Our most powerful microscope is not a lens, but a 27-kilometer ring buried beneath the border of France and Switzerland. The Large Hadron Collider is the ultimate expression of a simple, brute force idea. If we cannot find dark matter out in the cosmos, perhaps we can manufacture it right here on Earth. This machine represents the most direct assault on the mystery, a place where the frontiers of cosmology and high-energy particle physics violently collide. Inside its circular tunnel, protons are accelerated to 99.999991% of the speed of light, guided by superconducting magnets colder than the void of space. These twin beams, each carrying the energy of a high-speed train, are then steered into a head-on collision at 4 specific points around the ring. In these fiery moments, the concentrated energy recreates for a fraction of a nanosecond, conditions not seen since the first trillionth of a second after the Big Bang. From this primordial fury, new particles can flash into existence, governed by Einstein's famous equation, energy converting directly into mass. The hope is profound that among the spray of known particles like quarks and photons, something entirely new and invisible might be born, a dark matter particle. The challenge, of course, is detecting something that does not interact with the detectors. Scientists do not look for a dark matter particle itself. They look for its ghostly signature in the aftermath of the crash. It is a cosmic accounting problem. Before the collision, we know the total energy and momentum of the two protons. After the collision, physicists meticulously catalog every single particle that emerges, summing up their energies and directions. If a significant amount of energy and momentum simply vanishes, going unaccounted for in the final tally, it is a powerful clue that something invisible carried it away. This missing energy, this silent theft in the heart of the detector, could be the fingerprint of a dark matter particle fleeing the scene, oblivious to the complex machinery built to catch it. Experiments like ATLAS and CMS are exquisitely tuned to spot these imbalances. They have searched through billions upon billions of collisions, hunting for events where the visible debris jets off to one side, as if recoiling from an unseen force. So far, the dark matter ledger has balanced. No definitive missing energy signal has emerged. But this null result is not a failure. It is a process of elimination, ruling out certain masses and interaction strengths for potential dark matter particles. Each time the LHC upgrades to higher energies and intensities, it probes a new frontier of possibility. It is a testament to human ingenuity that we would build the most complex machine in history to try and conjure the universe's most elusive substance, not with magic, but with mathematics, steel, and an unwavering belief that if something exists, we can find a way to make it reveal itself, even if only by the empty space it leaves behind. The universe has a fundamental speed limit, and we cannot agree on what it is. This is not a minor discrepancy in the fine print. It is a full-blown crisis in cosmology known as the Hubble tension. At its heart is a single critical number, the Hubble constant, which tells us how fast the universe is expanding today. For decades, astronomers have refined two independent, gold standard methods to measure this number, and they are now precise enough to be in stubborn, undeniable disagreement. One path looks at the nearby universe using cosmic lighthouses called Cepheid variable stars. These stars pulse with a rhythm directly tied to their true brightness. By measuring their pulse rate and how dim they appear from Earth, astronomers can calculate exact distances to galaxies. Combine that with measurements of how fast those galaxies are moving away from us, and you get a direct local measurement of the expansion rate. This cosmic distance ladder, painstakingly built by telescopes like Hubble, gives us one very clear answer. The other path looks back to the infant universe, to the cosmic microwave background. The precise pattern of hot and cold spots in that ancient light is a snapshot of a young, dense cosmos. By plugging our best model of the universe, complete with dark matter and dark energy, into the equations, we can predict how that infant should have evolved. The model tells us exactly what the expansion rate today should be, based on the conditions 13.8 billion years ago. This early universe method gives us a different, equally clear answer. The problem is, these two numbers do not match. The local measurement says the universe is expanding about 10% faster than the early universe prediction suggests it should be. 10% may sound small, but in the precise world of cosmology, it is a chasm. It is like two impeccably calibrated clocks, one set by the birth of time itself and the other by the stars in our neighborhood ticking at different speeds. This tension means something is wrong. Either there is a hidden systematic error in one of our measurement techniques, which seems increasingly unlikely as both methods are cross-checked and refined, or our standard model of cosmology is incomplete. The recipe of dark matter, dark energy, and ordinary matter that so perfectly explains the cosmic microwave background might be missing an ingredient. Perhaps dark energy is not a constant but a dynamic force that changed strength over cosmic history, subtly altering the expansion story. Maybe dark matter has properties we have not accounted for, an ability to interact with itself or with dark energy in ways that tweak the universe's growth. Or perhaps something entirely new is at play, a relic particle from the Big Bang or a subtle feature of space-time itself. This is not just an academic debate, it is a direct challenge to our understanding of cosmic evolution. The Hubble tension is a crack in the foundation, and through it, we might finally glimpse the new physics waiting in the dark. The cosmic rain falling through you might hold a secret written in the bones of dinosaurs. This is one of the most speculative and fascinating connections in all of science, a hypothesis that ties the invisible architecture of our galaxy directly to the rise and fall of life on our planet. It proposes that dark matter could be a silent player in Earth's history, potentially responsible for some of our planet's most devastating mass extinction events. The story begins not with a dinosaur, but with the Milky Way's structure. Our galaxy is not a flat, uniform disk of stars. Research suggests that the dark matter halo enveloping everything is also not perfectly smooth. Instead, it likely contains a denser, thinner disk of dark matter, aligned with the plane of the Milky Way's visible spiral arms. As our solar system orbits the galactic center, it does not travel on a perfectly flat path. It bobs up and down, weaving through this plane like a car on a winding road. Roughly every 30 to 35 million years, our entire planetary system plunges through this denser dark matter disk. Now consider the frozen frontier of our own solar system, the Oort cloud. This is a vast spherical shell of icy planetesimals, cometary nuclei, located far beyond Pluto. It is a gravitational reservoir of ancient ice, and it is held in a delicate balance by the Sun's distant pull. The hypothesis suggests that when the solar system passes through the dense dark matter disk, the extra gravitational tug from all that concentrated invisible matter could be enough to perturb the delicate orbits of these distant, frozen objects. It would be like shaking a tree heavy with fruit. Some of these icy bodies get nudged out of their stable orbits and sent on a long, slow fall into the inner solar system, becoming the long-period comets we occasionally see. A small percentage of these could be on a collision course with Earth. The timing is eerily suggestive. Paleontologists studying the fossil record have long noted a possible periodicity in major extinction events, a pulse of catastrophe roughly every 26 to 30 million years. The correlation with the solar system's galactic oscillation is striking, though far from proven. It is a cosmic clock with a potential dark matter hammer. The mechanism is beautifully simple in concept, a gravitational ripple from the largest scales imaginable cascading down to trigger a single, world-altering impact on a pale blue dot. A comet, dislodged by an invisible force we are still struggling to detect, travels for millions of years before its light flashes in the atmosphere of a world ruled by giants, its impact casting a long shadow that resets the story of life. This idea remains a fringe hypothesis, a tantalizing what-if that is incredibly difficult to prove. The dark matter disk itself is a prediction, not a confirmed observation. The periodicity in the fossil record is still debated. Connecting one specific impact to a specific galactic passage is likely impossible, yet the power of the idea is undeniable. It weaves together the grandest and most intimate scales of reality. It suggests that the silent, dominant component of the universe may not be a passive backdrop, but an active agent in the narrative of life, its gentle gravitational hand capable of reaching across light years to tip the scales of evolution. Our very existence as a species, rising after the dinosaurs' demise, could be an indirect consequence of our galaxy's hidden geography. It forces us to ask a profound question. Are the chapters of life on Earth written not just by terrestrial forces, but by the invisible tides of the cosmos itself? The silent clock of extinctions and the discordant hum of the Hubble constant are more than isolated puzzles. They are symptoms of a deeper fracture. This brings us to our final, and perhaps most profound fact. The true nature of dark matter and dark energy is the greatest unsolved problem in all of physics. It is not merely a gap in our knowledge waiting to be filled. It is a chasm that threatens to swallow our most successful theories whole. Solving this mystery will not be like adding another room to the house of science. It will require us to rebuild the foundation. For over a century, we have lived with a cosmic schizophrenia. In the realm of the very small, atoms and particles, the bizarre rules of quantum mechanics reign supreme, a world of probability, entanglement, and uncertainty. In the realm of the very large planets and galaxies, Einstein's elegant theory of general relativity describes the smooth curvature of space-time by gravity. Both theories are spectacularly successful in their own domains, but they are fundamentally, violently incompatible. They speak different mathematical languages and break down when forced to describe the same event, like the singularity inside a black hole or the first instant of the Big Bang. Dark matter and dark energy sit squarely in the middle of this conflict. They are phenomena observed on the grandest cosmic scales, governed by gravity. Yet their ultimate explanation almost certainly lies in the quantum realm, in particles or fields we have never detected. To understand them, we must find the bridge. This is why the hunt is so urgent. Discovering what dark matter is, whether a WIMP, an action, or something even stranger, would be our first direct evidence of physics beyond the standard model, a tangible piece of the puzzle that could guide us toward a theory of quantum gravity. Unraveling dark energy, whether it is Einstein's constant or a dynamic quintessence, will tell us if empty space itself has a quantum structure we do not yet comprehend. The answer will force a rewrite of the cosmic story, from the first fraction of a second to the final fate of all things. It promises a unification, a single, coherent framework to describe everything from the spin of an electron to the expansion of the universe. We stand at a precipice armed with deep underground laboratories, space telescopes mapping the invisible, and colliders recreating the birth of time. Each is a different path up the same mountain. The view from the summit will be unlike anything we have ever seen, revealing not just what the universe is made of, but why it is made that way at all. The dark holds the key to the light, and we are finally learning how to turn the lock. From the quantum foam of the Big Bang to the silent rain falling through us now, these 25 facts are not just a list, they are a single, unfolding story of discovery. They paint a portrait of a universe where everything we see is the exception, and the true architects of reality remain phantoms in the dark. We have traced the invisible hand that sculpted the cosmic web, felt the repulsive force tearing space itself apart, and confronted the staggering possibility that our most cherished laws of physics are incomplete. This journey reveals a humbling truth. The greatest scientific revolution of our time is not about what we know, but about the breathtaking scale of what we do not. Yet this ignorance is not a dead end, it is an invitation. Every unanswered question, from the nature of the WIMP to the fate written in dark energy's equation of state, is a frontier waiting for a human mind to cross it. The same dark matter that guides the destiny of galaxies also mingles with the atoms of your body in this very moment. The same dark energy that will decide the final fate of all things is stretching the space between the stars you gaze upon tonight. So the next time you look up at that starry sky, remember, you are not just looking at points of light. You are seeing the glittering decoration on a dark cathedral built by forces we are only beginning to name. You are witnessing a mystery in progress, a cosmic story still being written, and we all have a front row seat. Which of these 25 facts reshaped your view of the cosmos the most? Share your thoughts below, and if you hunger for more journeys into the unknown, subscribe to keep exploring the deepest mysteries of our universe together.